So this is the module 2 of the lecture 25, the partitional unsupervised clustering. And in the module 1, we introduced the basic algorithm of k-means. So in this module 2, we will explain about the time complexity of k-means and also the theoretical foundations of k-means. Okay, so let's get started.
So OKNP is about reassigning cluster. ONP, yeah, it's ONP. It's the recalculating the center. And you also have 2 times because this dominates this. So KNP dominates the NP. So in the summation, because it's an iterator, right? It's a summation relationship. And the dominating cost is reassigning the center is the dominating cost. And then you don't do it only once. You actually do it many, many times. Assuming L times L, and then the whole cost is O, L, K, and P. But there's a good thing is, so let's compare this to hierarchical clustering. So if you remember, the hierarchical clustering is N cube P. And let's look at this number. N cube versus L, K, and N. So because they both have an N, it's canceled out. And then really the comparison is N quadratic versus LK. So you always has K much smaller than N, right? Of course, and this is a clustering. And then it depends on L, right? L is normally much smaller than much smaller than N2. It actually k-means converge very fast. So this is a much smaller number for the normal size of the objects, and that's the reason why the k-means it's a much computationally efficient method, less costly method compared to the hierarchical clustering. Question about this? And also the K is what you define, right? You decide. K is, if you in a normal algorithm setting, K is a constant. I can even cancel K out. It's only a constant. It doesn't grow with my data. Which makes the whole method actually depends on L, the convergence number of iteration. And k-means, in fact, is a special case of a method called expectation maximization. EM method is guaranteed to converge. In the most data, it converges very nicely. And there's an extra slide about EM. You can just read it. All right. So so here I copied the hierarchical clustering we had before. So feel free to do 1 versus 1 comparison versus the k-means versus the hierarchical clustering. If you still remember, the bigger cost in the hierarchical clustering is you have to calculate this matrix. This is called a rematrix calculation. And then when you have the matrix, you need to calculate the best cluster for my current state, right? So the majority of the cost actually, in fact, it's in the recalculating of the pairwise distance matrix. This is the dominating cost, and this is quadratic. And because the hierarchical clustering, you have to do so the bottom-up version, you have to do many times to group all the objects into one cluster, which makes the number of merging operation is proportion to the n. So that's the reason why there's an n quadratic cost in the matrix calculation, then there's n total of rematrix cost, rematrix iteration. So that's the reason why actually you need to have, if doing naively, it's an n cubed cost. So this is n quadratic. For each, there's the best cluster, it's almost n quadratic. And then you also have plus there are n minus 1 merging operations in, and that's almost like iteration in the k-means, right? And this merging operation in hierarchical clustering grows with the n, which is also a very big differences versus k-means. So that's the reason why the naive method is n cubed times p. I should write p there. Yes, this is actually p. Yeah. All right. Question about this? Oh, this is too confusing. Yeah. So you can actually tell I really like to do time complexity analysis of method we learned. The reason is I feel, so in the end, machine learning, it's more, it's a hot pot for handling data, right? There's all those different kind of properties you add on top of the method. You either add, you make it faster, that's one way to make it better, or you make it more robust, that's another way to make it better, or you make it more fair, that's like a third way to make it better. And as a computer science scientist, what you learn a lot before is, data structure, coding, and algorithmic solutions. Those all equipped you with a very good direction is to make it the machine learning method more actually faster, because the things you learned, it really equipped you with the skills. But how do you make it faster, right? You have to analyze it first, right? You have to understand who's slow, who is not slow. And that's the reason why I kept trying to analyze all this and also compare. But of course, this is only just one perspective to analyze all those methods, right? There's another perspective. So if you are statistically trained, you got a lot of training in probability, in mathematics, in basic math. And then those type of skills will help you understand how the function you want to learn truly matches the data better. So that's the reason why in the statistics field, they actually have a big focus on error bound analysis, right? Because the skills they learned equip them with those necessary tools to help them to analyze those. I mean, later if you try to, in your research or maybe in the jobs, I mean, you have to consider what is my niche? What have I learned before? It's something needed, something necessary, or something can be improved. It's my niche, even can improve something of this, the thing I care. So if machine learning is what you care, think about your niche, your skill sets. It's your skill set, algorithmic analysis. Then scalability is a very good direction. If your skill set is mathematics or information theorem or statistical analysis, then theoretical error bound analysis are good direction for you to improve. And then it's really in the end, so there's a reason why I'm doing this, because I feel like the majority of the students here are more computer science oriented. So maybe scalability is your niche. You think about you're going to work in your future jobs and how to scale up some simplest method into many, many data. And doing this type of analysis is the first step to realize, okay, is some parameters, some variables are the bottleneck, to hinder that method to scale up, right? So I hope this, whatever analysis I did before, give you a sense of this type of research, and I hope you understand why this cube P, and I can repeat this because I really want you to get it. Okay, so if you still remember what is hierarchical clustering is you have a pairwise distance matrix of all the data points in your data. So this is already much more computationally costly than K-means, right? In the K-means, what do you even need to do? You only need to calculate every point to the center. You only need to calculate every point to the center. And there's only K centers. But in the hierarchical clustering, you have to calculate every point to all the other points. And this is already much more computational costly. Okay. And then the recluster has a little bit, so those are more details. So after you know the best cluster, in this case, you group 1 and 2 together. And then your current cluster is 1, 2, 3, 4, 5, right? And then you need to rematrix this old matrix into a new matrix, and to calculate the cluster 1, 2 versus 3, 4, 5. Because that's a new cluster. You have to recalculate this distance, right? And then because of the size of that cluster, it's upper bounded by ON. And then for the rest of the points, it's also upper bounded by ON. Equivalent to, I'm calculating 1, 2 cluster, this size N versus, this is really what I wrote here. So I'm trying to calculate this new cluster, treat it as a new point. This point versus all the rest of the points, the distance. And if this is only a point, the calculation is very simple. It's just the point versus the other points, right? But the problem is this is a cluster and it's size N. No matter what single link, complete link, or average link you're doing, you have to calculate 2 versus 3 to 4 to 5, and 1 versus 3 to 4 to 5, and then compare. The single link is to get the smallest, complete link is get the largest, average link is get the average. So in the end, you have to calculate this versus everything from the rest. And this size is upper bounded by ON, and this size upper bounded by ON. This is a pairwise combinatorial operation. That's why reclustering cost is ON quadratic. And then you have to do this rematrix operation for n-1 merging operation, because you want to merge everything into one thing. It's just, the more data you have, the more merging operation you need to conduct. So that's the reason why it's hierarchical clustering, just intuitively, it's much, much more computationally costly than the K-means. All right, okay, so enough for this, and then let's now see why K-means converges nicely. So from the beginning, we talk about what makes a good cluster is we have an intuitive definition is want to maximize the within cluster similarity, want to minimize the between cluster similarity. And how do you even represent it in the grouping case, right? So in the K-means, it's actually very, very intuitive, because we're trying to minimize points versus the center distance. And that's really just So I'm now, because I need to represent center, right? So now let me use notation C to represent each center. And then the distance is each xi minus the center, and then take quadratic. It just, in this case, it just, Euclidean distance. And then there's an indicator function called Mij you need to introduce. It introduces just the cluster membership. If the points belongs to C1, that notation equals to 1. If the points doesn't belong to the cluster, that notation equals to 0. So this really just shows what's the within cluster similarity measure, and then sum over all the clusters. If the points doesn't, assuming let's use a point as example, so this specific point, it belongs to C2, it doesn't belong to C1, so that's why the I is so this is the xi point, mi1 equals to 0, mi2 equals to 1. And it's really just the contribution of this point into that cluster is 0 because it's not in the cluster at all. So it's just equivalent to I only just sum whatever points belongs to my cluster, and I'm summing over all the clusters together. So this is a very intuitive definition of within cluster similarity. I'm trying to within cluster similarity, then my goal is to minimize the within cluster similarity. But from the beginning, what you are given is only just x. You don't have anything else, right? You have only x. You don't know c, you don't know m, and those are the parameters you need to search. So my goal is minimize the within cluster distance in this case, and then it's represented by this function, and then there are two sets of parameters. The first parameter to look for is the center. The second set of parameter is the each point's class membership assignment, which is n. So, and now, okay, we're coming back to what we started from the beginning, right? Every machine learning method can be written as a loss function, and we are minimizing a loss function. We are minimizing within cluster distance in this case. But our parameters, our unknown parameters are much more complicated, which is C sub G. There are a total of K C sub G centers to look for. There are a total of, actually Mij is n times P. This is a matrix. M here is actually a matrix. It's n times actually K. M is a matrix. It's n times K matrix. If you write it as a matrix form, is the first I is n, and then the second is K. So this is my parameter to look for. There are n times K parameter to look for. And you actually can do that very easily. Again, our old trick. Set it to gradient S0, set the loss function versus one of the parameter partial positive, partial derivatives at 0, and you solve it. The issue of this two sets of parameter is, okay, so the solution, if you do this partial gradient, partial derivative at 0, the C parameters uses M in its solution. And the M uses the C in its solution, because both C and M are unknown. There's no way if you just directly solve it, because C uses M uses C. And there's no complete solutions at all, because I don't know M, I don't know C. And then what can you do? And then the solution is, okay, let's do an iterative fashion. Let's assume M is known. When you assume M is known, you can solve the C. When you assume C is known, you can solve the M. And that's actually solved the whole iterative solution. But you have to assume M is known or C is known, right? And then that gives you the solution, which is iterative K-means. So in the beginning, because of these two sets of parameters are correlated, you have to know one part to solve the other part. And that just gives you the solution has to be an iterative method. And you assume the center are known, and then you solve the best solution is exactly the current K-means solution. Okay, I know the C, I know the center. When the center are fixed, each point, the cluster membership is whoever is the closest, whichever center is the closest to this point is the membership assignment, which exactly is the assignment stage in the K-means. And when the M is known, which is the state, right? Okay, you assign every point into a certain cluster. And now when you know the membership, the best class center is just whoever belongs to that center, the mean, which is exactly the solution. If you look at the solution is, the upper is Mij times Xi over the summation of Mij. So this is, the upper is whoever, because Mij is a binary variable, right? Whoever doesn't belongs to the J's cluster, the Mij will be 0, right? And then this makes what? The upper is only those points belongs to the J's cluster. You just sum them together. And the lower is whoever doesn't belongs to this current cluster, it gives you 0. And only those belongs to the cluster give you 1, right? This is exactly the size of that cluster. And this is exactly in the step of K-means is calculating the mean operation. So, and the whole thing I could give you, K-means is not an arbitrary method. In fact, it's a method just because the membership and the centers are correlated. So that's why we're trying to solve this loss function through because of the two correlated parameters. We have to solve it through an iterative method. The question is it because we use Euclidean distance, that's why it converges? Actually, no. The reason why it converges is because this is a special case of a method called EM. And EM is proved to have good convergence behavior. And that's actually related to some much more complicated concept I covered it in the lecture 19D about the EM. So feel free to check it out if you want to read EM. All right, so K-means is a special case of expectation maximization algorithm. EM is known to converge, and the number iteration could be large, but in reality, it depends on your data. And in most cases, it actually converges pretty fast. All right, so this is about the theoretical, a little bit theoretical analysis about convergence. And K-means it's not like hierarchical clustering. We don't have a global loss function to optimize. Actually, in the K-means case, we have a global function to optimize. But the specific optimizer is an iterative method because there are two sets of parameters and the parameters are correlated. And you have to use an iterative method. Okay, so so this is actually about convergence. I'm going to skip it. Feel free to read why. It optimizes a goodness measure. So you can actually prove it monotonically decrease that goodness measure, and so feel free to read the previous proofs. Okay, so now the question is, how do you pick the starting position of the clusters? The seeds is actually somewhat critical. So people normally just use random restart. You can have multiple rounds of restarted because in the end, EM doesn't converge to global solutions. It's a local solution. It's an optimizer, give you local optimal solutions. It doesn't guarantee give you global optimal solution at all. And this means what? If you started from a really bad starting point, it might converge to a bad local optimal solution. But this is kind of similar to stochastic gradient descent, right? We had that kind of issues before. The starting point is somehow critical. But it's easy to solve. You just restart. You do random restart for a few times. Okay, so to summarize, K-means just perform the basic grouping operation. It just partitionally group into multiple groups. It has this assumption called a mixture of spherical shapes. So this maybe sounds kind of magic now. We're going to talk about in the next few slides. The basic assumption in K-means is it's a spherical shape. It doesn't consider the covariance of the oval shape at all. It's a sphere. The basic assumption is each center, each cluster is a sphere. And the loss function you are optimizing is sum of a square distant to the centroid. And the method is an iterative method. It's a special case of EM. And then the model is the cluster membership and the centroid, which is represented as Mij and Cj. And their Mij is n times k matrix. Cj is, each Cj is a p-dimensional vector. And there are a total of k Cj vectors. All right. Okay, so then the simplest question now we need to ask is how to pick k. So actually, it's very difficult to pick the right k. So there are many approximation methods. So let's just introduce one of the methods. So when k equals to 1, you got this that objective function, right? Summation of distance to the centroid. And then you can keep adding k, make k bigger. And there's something called knee finding or elbow finding. It normally has this drop of the objective function, and then it reaches a plateau. And you can think about that plateau stage means it's not improving anymore. And this knee point is the best point. So intuitively, it's a good solution. It's an okay solution. So in the homework, if you want to do the actual credit, so this it's actually pretty easy to use the knee finding or elbow finding to figure out the right k. Question about this? And just to let you know, this is a very easy case. So that's why you got a very clear plateau, a very clear drop, and then the plateau shape. But in a lot of real problems, it's not as clear as this. Sure.
Generally, we kind of like see this from the graph and interpret it, right? So there is no like mathematical formula to find the knee or something.
Yeah. So how to find the best k, right? The question is, are there mathematical methods? There are actually a lot of methods proposed. So for the classic maybe topic model, if you think about what is topic modeling. Topical modeling is group the documents into topics, right? And how many topics? And there are a lot of Bayesian type of method. So adding the Dirichlet prior, I don't want to talk to the rest of the class. So there are a lot of Bayesian type of method being proposed to figure out the right number of clusters. There are a lot of prior type of probability formulation. There's something called Indian buffet process or Chinese buffet or Indian restaurant. There are many, many prior type of probability function proposed. So it's a huge, it's a huge topic. How to figure out the right number of clusters. Yeah. All right. So again, so even if you already got a K, you have a good elbow or good knee positions, but you still need to measure, right? How to measure the final clusters. And actually, it's very similar to what we had before in the decision tree of the final leaf nodes. So what makes a good leaf node in decision tree? As pure as possible. In a clustering case, it's similar. If you know the labels of the clusters and you want to look for those clustering results as pure as possible. That really just there are many, many different measurements you can use, even the Gini and entropy or the specific called the purity method we can use here. It's very, very simple. It's you really just use the maximum number of that cluster over the total size, and it shows how pure is my current cluster. And consider all the cluster, you sum them together. This is the only one choice. There are many, many possible other choices we learned. It's a similar task. It's a very similar measurement as decision tree, the leaf picking. So so this is purely easy. Let's just see the purity of class 1. We just see we do assuming. So here in the end, the first question is how do you even know the color? The color here is actually you know they are class labels. And this sounds pretty odd, right? So you already know the class labels. Why do you even cluster them? Why not just learn a predictive model to directly predicting? So there are a lot of arguments actually in the literature about. So some researchers think this kind of unsupervised method is can maybe learn more than predictive models, but you can use those class labels as a validation of the cluster outputs. So that's a lot of arguments from that crowd. I'm not completely agree with those because I'm more in the predictive tribe. So in the end, you can tell I always feel clustering method. It's a very subjective operation, and you can use those more like a filtering type of operations. But it's just in the end, the most difficult part of clustering is how do you even know the quality of clustering? It's extremely difficult because you don't really have a good measurements at all. And in the K-means case, you minimize that summation of the points to the cluster center, but there you actually have a good assumption is Euclidean distance or whatever distance measure is a good measure. It's very questionable is that that's a good measure if you have certain goals in mind. But so for the homework, you just use this. I mean, you can also use Gini if you know how to calculate Gini. It's the P times 1 minus P. It's also a very good measure.
Great. So this is the end of this module. See you in next module.